Hello students, welcome back. I am Rinkesh and today we are going to continue with chapter number 4, that is Principle of Mathematical Induction. Okay, today we will solve the sum related to the multiple or divisibility, and today we will complete this chapter. So let's start. Let's start with question number 20. You have to prove that 10 raised to 2n minus 1 plus 1 is divisible by 11. Okay, so first for e of 1, 10 raised to 2 into 1 minus 1 plus 1. So that will go 10 raised to 2 into 1, that is 2, 2 minus 1, 1. So 10 raised to 1, 10 plus 1 equal to 11. So obviously 11 is a multiple, right? 11 is a multiple of 11, hence I can write down which is divisible by 11, hence p of 1 is true. Let p of k be true. Okay, so it will give us that 10 raised to 2k minus 1 plus 1 is divisible by 11, so I can write down this as short as that will be equal to 11 lambda. Okay, we have named this one 11 lambda. Now we are going to use this equation. How we are going to use that, we will see later. Now for p of k plus 1, we have to prove 10 raised to, here I will use 2 into k plus 1, that is 2k plus 2 minus 1. So 2k plus 1. So plus 1 plus 1 is divisible by 11. Here, so let's take now 10 raised to 2k plus 1 plus 1. I can write it down this as 10 raised to 2k minus 1 plus 2. I had arranged this 2k plus 1 as 2k minus 1 plus 2. Why I had done? Because I am having here 2k minus 10 raised to 2k minus 1 plus 1 as it is. So now I will write down, I will separate it, 10 raised to 2k minus 1 into 10 square. So 10 square into 10 raised to 2k minus 1 plus 1. So what I require here, 10 raised to 2k minus 1. So I will arrange it here like this way. 10 raised to 2k minus 1, that will be equal to 11 lambda minus 1. Now I name it as 2. Yeah. So now what I will do, instead of 10 raised to 2k minus 1, I will put 11 lambda minus 1. 11 lambda minus 1 plus 1 as it is. Okay. So let's multiply 10 square into 11 lambda. 10 square into 11 lambda minus 10 square into 1, so that is 10 square, that is 100, 100 into 1, 100 plus 1. So this will be 10 square into 11 lambda minus, see I can multiply this 10 square like 100 into 11, 1100. Okay, or I can add on this one, minus 11 100 my plus 1, that is minus 99. So now I can take 11 common. So what will be equal to 10 square lambda minus 11 nines, because I had taken 11 common. Okay, so now see, I had taken 11 common. So what does this mean? That this number is multiple of 11. I can write down which is divisible by 11 because it is a multiple of 11. Okay, hence P of k plus 1 is number 2. Therefore, according to principle of mathematical induction, P of n is true for every n belonging to n. Yeah. So remember P of 1 I had first proved it. Okay. P of k I had assumed it and just taken as it is must be divisible by 11. I have taken 11 lambda. Now for P of k plus 1 we need to prove this. So what I did, I rearranged this in form of 10 raised to 2k minus. I replaced the value and finally I took 11 common. Yeah. So this was about question number 20. So just note it down. Now let's see the next, that is question number 21. Question number 21, you have to prove that x raised to 2n minus y raised to 2n is divisible by x plus y. Okay, so for first p of 1. For p of 1, what we will take? X raised to 2 into 1, that is 2, minus y raised to 2 into 1, that is 2. Right? So this is x square minus y square. So this will be x plus y, x minus y. Obviously, I got x plus y here. So this is multiple of x plus y. Hence, I will write down which is divisible by x plus y. Okay, so p of 1 is true. Now let p of k be true. So what will that imply? X raised to 2k minus y raised to 2k, that will be equal to x plus y into lambda, right? Means it is multiple of x plus y. So what I can do here, let's take x raised to 2k separately. This will be equal to x plus y lambda plus y raised to 2k. Let's name this as equation 2. Okay, similar to question 20. Now this x raised to 2k I will use in the next part, that is for p of k plus 1. Now for p of k plus 1, we have to prove x raised to 2 into k plus 1, that is 2k plus 2, minus y raised to 2 into k plus 1, again 2k plus 2, is divisible by x plus y. Okay, so now let's take this x raised to 2k plus 2 minus y raised to 2k plus 2. So what I will do, I will separate it. X square into x raised to 2k plus y square into y raised to 2. Clear? So see, base same 2, 2k, 2k plus 2, 2k plus 2. So now what I will use, I will use this x raised to 2k. Instead of that, I will put this x square into x plus y lambda plus y raised to 2k plus y square into y raised to 2. Clear? So now let's multiply x square into x plus y lambda. X square into x plus y lambda plus x square into y raised to 2k. plus y square into y raised to 2. Right? So what you can see here y raised to 2k and y raised to 2k. You can take that common. Okay. So what will be our next step? X square into x plus y lambda plus y raised to 2k common. I will get x square plus, sorry, my mistake. Here it's minus. This is minus and I put here minus, minus, minus. So it will be x square minus y square. What is x square minus y square? X plus y, x minus y. X square, x plus y lambda, y raised to 2k, x plus y, x minus y. So now see, x plus y and x plus y I can take common. So this will be equal to x plus y into, so what is remaining? X square lambda plus y raised to 2k into x minus 1. You can see here x plus y, so it's a multiple of x plus y, so I can write down which is divisible by x plus y. So p of k plus 1 is true. 3. Hence, according to principle of mathematical induction, P of n is true for every n belonging to n. Clear? So this was about question number 21. So just note it down. Now let's move to the next, that is question number 22. Question 22. You have to prove that 3 raised to 2n plus 2 minus 8n minus 9 is divisible by 8. Okay, so let's take for p of 1, 3 raised to 2 into 1, that is 2, 2 plus 2, 4, minus 8 into 1, minus 9. Clear? 3 raised to 4, that is 81, minus 8, minus 9, that means minus 17. Clear? So 81 minus 17, this will be equal to 64. And 64 is divisible by 8, right? Which is divisible by 8. Hence, P of 1 is true. Now, let P of K be true. Okay, so what will that mean? 3 raised to 2k plus 2 minus 8k minus 9. This will be equal to 8 lambda. Okay, so we will be using this for the next part. 3 raised to 2k plus 2, that will be equal to 8 lambda plus 8k plus 9. Clear? Now for p of k plus 1, we have to prove 3 raised to, now see here, 2 into k plus 1, that is 2k plus 2 plus 2, so 2k plus 4 minus 8 into k plus 2, sorry, k plus 1, so that will be 8k Let us run k plus 1 minus 9 is divisible by a. Okay, so let's start with this. 3 raised to 2k plus 4 minus 8 raised to k plus 1 minus 9. Okay, this is equal to, now see what we want, 3 raised to 2k plus 2. So what I will do, 3 square into 3 raised to 2k plus 2, right? So base same, 2k plus 2 plus 2, 2k plus 4 minus 8 into k, 8k minus 8 into 1 minus 8 minus 9. Clear? So instead of 3 raised to 2k plus 2, what I will put, 8 lambda minus plus 8x plus 9 minus 8k minus 8 minus 9, that is minus 70. So this will be equal to, now let's multiply 3 square into 8 lambda plus 3 square into 8x. See, I'm not multiplying because I want this 8. Finally, I will take 8 common. Plus, now 3 square, that is 9 into 9, 81. Minus 8k minus 17. So 3 square into 8 lambda. 3 square into 8k. Sorry, it's not x, it's k. Okay. Minus 8k plus 81 minus 17, that is 64. So plus 64. Now I can take 8 common from here, from here, from here, from here. So this will be equal to, I can take 8 common, 3 square lambda plus 3 square k minus k plus 8 8 are 64. Now see here, I have taken 8 common. That means it is divisible by 8. Hence, P of k plus 1 is true. Therefore, according to principle of mathematical induction, P of n is true for every n belonging to n. Clear? This was about question number 22. Again, we use the same method. I proved P of k plus 1. Assume P of k as true and leave this equation 2. Then here I replaced. I can write down here from 2. Okay. Then I proved took 8 common. So this means it was divisible by 8. Clear? So note down question number 22. Just tell me when you're. Now let's move to the last sum. Okay, last is 24th, but 24th we had already completed in earlier video. So 23rd is the last for this exercise for us. You have to prove 41 raised to n minus 14 raised to n is a multiple of 27. So now first for e of 1. 41 raised to 1, that is 41, minus 14 raised to 1, that is 14, that is equal to 27, right? So it is a multiple of 27, which is a multiple of 27. Hence e of 1 is true. Now let e of k be true. So it will be 41 raised to k minus 14 raised to k, that will be equal to multiple of 27, so 27 lambda. Okay, we'll use our same technique, we'll use 41 point k, 41 raised to k for our next step. That will be equal to 27 lambda plus 14 raised to k. Let's name this as equation 2. Now, for p of k plus 1, we have to prove 41 instead of n, k plus 1 raised to k plus 1 minus 14. Instead of n, I will use k plus 1 is multiple of, okay, is a multiple of 27 here. So let's start with this. 41 raised to k plus 1 minus 14 raised to k plus 1. So what I will do, I have 41 raised to k, right, from equation 2. So I will separate it. 41 raised to 1 into 41 raised to k minus same thing for 14. 14 raised to 1 into 14 raised to k. Say, see, the base is same, so the power must be added, k plus 1. Here also base is same, so k plus 1. So now instead of 41, I will use this 27 lambda plus 14k from equation 2. So 41 raised to 1, that is 41. Instead of 41 raised to k, 27 lambda plus 14 raised to k minus 14 raised to 1, 14 into 14 raised to k. Now let's multiply it. 41 into 27 lambda. I will not multiply, just write down like this. 41 into 27 lambda plus 41 into 14 raised to k. 41 into 14 raised to k minus 14 into 14 raised to k. Here, so now see here, you can take 14 raised to k and 14 raised to k common. So this will be equal to 41 into 27 raised to lambda plus 14 raised to k. I will take it as a common. So 41 minus 14. So 41 minus 14, that is 27. So this will be equal to 41 into 27 raised to lambda plus 14 raised to k into 41 minus 14, that is 27. So I will take here common. What I can take common? I can take common 27 and 27. So this will be equal to 27 into 41 lambda plus 14 raised to k. Now see, as I had multiplied this with 27, it means it is a multiple of 27. So which is a multiple of 27. Hence, p of k plus 1 is true. Yeah, so therefore, according to principle of mathematical induction, P of n is true for every n belonging to n. Yeah. So here also first I prove that P of 1 is true, assume P of k is true, and got an equation. Now we need to replace this 41 raised to k in our further step. For P of 40, k plus 1 we need to prove this. So I separated it and I got 41 raised to k. And this was from equation 2. Finally I got that it is a multiple of 27. Yeah, so this was about question number 23. So just note it down. Okay, students, so that's it for today. Here we had completed chapter number 4 and exercise. Okay, thank you.